Hey everybody, happy Tuesday again. Here we are. So today what we're going to cover is we're going to finally get down to the details of how we implement indexing on disk drives for database systems, all right? So we talked sort of in the abstract about indexes last time. And of course, you may remember when we discussed joins, we had this black box called an index in the middle of index nested loops join. And all we knew about an index at that time was that you could do a lookup in it and get things back fast. So today we will delve in and demystify this. A quick review from last time, okay? Files, pages, and records, right? I think we actually did a pretty good job reviewing this last time, but I still want to just touch one more time because it'll ground our indexing discussion. So the abstraction of stored data is going to be files, all right, which are collections of records stored on pages. So there's files with pages or blocks of records. Records live on pages. The physical record ID, the way that you go find a record, is page number, comma, slot number. All right, that is the address of a record, and we know physically how to get it. It's at that particular page, and then at that particular slot on the page. Okay. If you have a file that spans multiple disks, there's probably embedded in that page number, there's a disk ID as well. Okay. Variable length data, you should remember, because this is the general case. To store fields in records with variable length fields, we'll have that list of offsets at the front of the record with the little pointers into the middle of the record to tell us where to go find field 1, field 2, field 3, and so on. And then, in a somewhat analogous manner, records on pages recall the slotted page organization, where at the end of the page we have the slot directory pointing into the storage area of the page where we have the records. If these are not familiar, you should go review them before you study up on this lecture on indexes. Now, generally speaking, we can be a little bit lazy about a bunch of the issues with space management in the database, kind of reorganizing tuples on a page, reorganizing pages in a file. We're going to be a little bit lazy about this and do it in batches, all right? You don't want to always be real, obsessive compulsive about making sure you compact everything, because there's a certain overhead to doing the compaction, particularly for things on disks, like reorganizing the pages of a file. So instead, what will happen is we'll let things get a little sloppy, and then in the background, periodically, we'll go through and we'll clean things up. Okay, so don't imagine in some of these organizations that they're always kept pristine. We talked about sort of 3 file organizations, unordered files, also called heaps. Remember, when I talk about a heap file in this class, I don't mean a heap data structure with find min. I just mean a collection of records in a file. We talked about sorted files that we really keep sorted, and basically we're not going to use those. But we looked at them in our analysis, so I do want to remind you that we talked about them. They're expensive, and indexes are a more flexible solution. So today's lecture on indexes will replace our discussion of sorted files. And then finally, last time we talked about kind of sorted files, which are clustered files. That's the word that's used in the database community, where they're mostly in the order of some search key, but over time, in the face of insertions, some rows may be out of order. And that'll be okay for a while. And then periodically we might want to go through and clean it up, either incrementally or in batch. Okay, and we won't worry too much about that background cleaning, but just be aware that a cluster file is not guaranteed to be sorted. It's just likely to be sorted. So it's more of a performance hint than a semantic guarantee. All right, and then we talked about, in the abstract, that there might be some file organization called an index that could speed up different kinds of accesses. And we talked last time about different classes of little queries that we could ask of these indexes that they might be able to answer. Sometimes in database systems, particularly in the earlier research literature, indexes are referred to as access paths to the data. It's just a phrase you may want to be aware of if you become a database insider. Okay, so today we're going to talk about tree-structured indexes, which are sort of the versatile, widely used workhorses of most database systems. So the selections in any index are going to be of the form field, operator, Boolean operator, constant, right? So examples of this might be the operator's equality, like department equals computer science. All right? Either tree or hash indexes will tend to work there. We won't study hash indexes in the class, as I mentioned, but there's a nice chapter in your book on linear hashing, which I encourage you to read. Range selection operations could be one of less than, greater than, or between, less than or equal to, greater than or equal to. Linear ordering queries. Okay? And hash indexes do not work for these because they're based on hashing. And of course, the whole name of hashing is that it makes a hash of an order, right? It messes up the order. So hash indexes won't work for range predicates, range queries. But these tree indexes we're going to look at will work for linear range queries. And then, as we said last time, you can have fancier selections, like, for instance, spatial containment or near neighbor queries. And there are indexes, typically tree-shaped indexes, that work for these. We won't study them this year in this class. I've done it in previous years, but it's a bit esoteric, and I think there are other topics in advanced material that we want to cover this year, probably like NoSQL and things like that may be more contemporary. So if you're interested in this topic, I gave you links last time. Tree-structured indexing techniques are going to support range and equality selections, and we're going to look at two techniques today. The first, ISAM, is of historical interest, and the only reason really to teach it is that it's a nice warm-up to really what we want to learn, which is B+ trees. Right? ISAM is an old IBM-based mainframe data structure. It stands for the Indexed Sequential Access Method, and you will see why it's called that, okay, when we look at the structure, which is both indexed and sequential. We'll talk about it in just a second. Okay, a note of caution. ISAM is very old-fashioned. We're talking like 1960s technology. All right? B+ trees are almost always better. Maybe not always, and we'll see exactly, ask the question, when are they not better? ISAM's a good place to start because it's basically the kernel of the idea of the B+ tree, which was invented in the early 70s, right around the same time that the relational model was invented, not probably coincidentally. They came kind of together. ISAM is easier to understand. So it's a way to get us towards B+ trees. We're actually going to go through history and learn the lesson in the same order that the community learned it. Right? It's just helpful. But you don't want to put on your resume that you know all about ISAM. It's not going to. It'll impress a very small number of people. I will say that old 1970s and 1960s IBM mainframe technology still powers some of the systems out there in the world. And if you're looking for a niche expertise, you can probably still make good money knowing about things like ISAM and VSAM and old IMS databases from IBM that predate relational databases. But it is a niche, and it is on its way out over decades. It's very hard to kill a database system in deployment. So they're still out there, but you don't want to brag about that. Probably you do want to understand them, though, and you want to understand how they trade off with B+ trees. Because if you really understand B+ trees, you'll be able to answer these questions about how they're different from ISAM, and you'll know that you know the material. Okay, so let's think about range searches for a minute, because it's sort of the extra power of a tree-shaped index over a hash index. So we want to find all students with GPA greater than 3.0. So if we had a sorted file, we talked about this 2 lectures ago, the way we would do this is we would do binary search in the file to find the first record, right? And then we would scan to the right. Yeah. Find the GPAs that start with 3.0, and you scan to the right, and you get higher and higher GPAs. All right, so the cost of binary search in a database, though, is kind of a bummer. Why is it a bummer to do binary search in a database as opposed to, say, in memory? Yeah, random disk access is very expensive, as we talked about, right? And binary search, while it's very nice, is binary. It's only carving things into 2 each time. Maybe we can carve it into a larger constant than 2. Wouldn't that be nice? Because the constant factor of going to the disk drive is so high that we want to amortize that cost somehow. So the simple idea, if we have this data file, instead of doing binary search in this sorted file, we'll create an index file on top of it, right? It'll kind of look like this. And it's going to allow us to do a much more efficient search, because we're going to do binary search in our little index file. And the index file is going to contain pointers to the pages of the sorted data file. And it's going to contain keys that tell us the lowest value on the page whose pointer is to the right. So K1 is the lowest value on page 2, which means anything less than K1 is on page 1. Right? Kn is the lowest value of anything on page n. Okay? And we can do binary search in that index file, but the index file, which still may take many disk blocks, so each one of these inner rectangles is intended to represent a disk page, the outer rectangle to represent the file. The index file doesn't store entire records. It only stores the key values and the pointers to the pages, right? So you may have a record with 10 columns, and this is only storing, say, the GPA field, which is just a float, right? So the index file is going to be quite a bit smaller to search in than the data file. So that's idea number 1. Let's at least do binary search on something smaller. Okay. And you have that idea, and you say, hey, wait a second, I could do that recursively. Why don't I build an index file for my index file? Right? And that's roughly what an ISAM is. So what an ISAM is, it's going to be a hierarchy of these index files forming a tree. And then in the leaves, we're going to have a sorted file. Okay? Sort of. All right, and that's going to be where it gets a little bit fancy. It's not at all fancy. It's actually stupid. But you'll see where it's different than a plain old sorted file. So the leaf pages are going to contain the data entries, and the non-leaf pages are going to be this hierarchy of index pages that let us navigate down to the leaf pages. So let's see how this works. And again, 1960s technology. Each one of these internal nodes, these non-leaf pages in this index, is a disk page. All right, keep that in mind. These are all these little rectangles on this are disk pages, which contain 64K of data. Okay, and an index page, a non-leaf page, is going to look like this. It's going to have a set of index entries, key, comma, pointer. So K1, P1, that pair is an index entry. All right? And it says that everything, if you follow pointer 1, will be K1 or greater. Right? And everything, if you follow pointer 2, will be K2 or greater. Right? So the things between P1 and P2 are down, the things between key 1 and key 2 are down P1, and so on. Right, so those are the index entries, and that's the structure of a non-leaf page. Right? And so here's an example of a dorky little ISAM that fits on screen. The whole idea here, right, is that these pages are very big. 64 bytes worth of these little pairs is a lot, maybe a couple hundred of these index entries on a single page. Okay, but just to make this visible on the screen, we've got 3 index entries, 3 pointers per page internally, and 2 values in the leaf level. Okay, so it's very small. So here's an example where each node can hold 2 entries, and you can see things that are less than 40 are to the left, things that are greater than 40 are to the right, and then recursively, less than 20 is over here, 20 or greater is here, 33 or greater is here, 40 or greater is here, 51 or greater is here, 63 or greater is here. And you can see how you would navigate this tree pretty directly from the root to the leaves to find a value. Now, these are the index entries, right? Search key value, comma, page ID. So I've highlighted an index entry there. And there are many of these, obviously, on each page. And here's a path of index entries to get to a leaf. But I want to point out one thing, which is that implicitly, there's an index entry at the left of each one of these as well, which is negative infinity, comma, pointer. So anything greater than negative infinity is, and less than 40 is down to the left. We don't have to store negative infinity. It's implicit, right? So it's as if we've compressed it away. But sometimes people get a little confused when we talk about the index entry being a search key value and a page ID. We're getting that leftmost search key value for free, right? So there's one more pointer than there really are search keys on the page. Make sense? And obviously every page you can think of as having negative infinity off to the left. Right? Okay. Now, ISAM is a static structure, which is why it kind of feels like 1960s technology. It's that whole tree shape is created when you create the file, and it never changes again. Which seems kind of crazy, right? So here's how the way this works. We create an ISAM file like in batch from a batch of data. So you have a big table, which hopefully won't change very much in the future, right? And you take that table and you sort it by the search key that you like. And you store that at the head of your file. So the first however many pages of your file are the data pages. They are the leaf level in sequential order on the disk. So this picture off to the right, if you want to think of it as the blocks of that ISAM file, the first number of blocks is the data pages. It is that leaf level stored in sorted order. Okay, up on the top right of the screen. And then what we're going to do is we're going to construct the upper levels of the tree and append them to the end of the file. So the file will contain first the data and then the index level. Okay? And at the end of that structure, we've built the data in sorted order and then appended the index pages after it. Anything that happens later on that needs to be added to this index will be appended at the very end of the file in these overflow pages. And I'll show you how this works. All right, so that's the physical structure of the file. And you can see why it's called indexed sequential now. It is an index, but the data is actually stored sequentially in the head of the file. If you need to scan the data, you don't pay for the index at all. You just scan the data pages, and they come in order. So it's very dense, actually, representation up at the front, right? It's just the data in sorted order. If you want to use the index, it's off in the middle of the file somewhere, and you can go find it. Okay, probably have a pointer to the start of the index. All right, so search obviously starts at the root, so you need to know where the index pages begin, because that's where the root node's going to be. And then you use these key comparisons to walk down to the leaf. Remember that every pointer in this picture is a disk block address. Right, it's a disk-based data structure. So where you see a pointer here, that's a disk block address in that file on the upper right here. So all you need to know is where the index page root is, and then everything else you'll navigate by following these pointers, which are disk block addresses. And you'll go accessing blocks in the index pages as you navigate this file. Oop, that's exciting. We'll do that in a second. So search is going to start at the root and use the key comparisons to go to the leaf. Obviously, search is cost log n, and the it's log base f, right? The base of the logarithm is f. F being the fan out of the page, the number of entries per page, the number of pointers per page. Okay? Which is much better than log 2. F is going to be like 100 or 200, which is a big deal, actually, turns out, in practice, okay? It's not a big deal in big O notation. It's a big deal in practice, though. Constant factors matter to us quite a lot here because IOs are so expensive. All right, so F is the number of entries per page, really the number of pointers you can think about. N is the number of leaf pages, okay? Now, there's no need for the leaf pages to be linked together. Why is that? We don't need to store pointers at the leaf pages. Why don't we? If we want to scan across the leaf of this index, how do we do it? Okay, one idea, breadth first search. We could not scan the leaf of the index. We could wander around and visit the leaf of the index using any search algorithm you like. You could do that, but that'd be very expensive, a lot of random I/O. Yeah? Exactly. We know where the leaf pages are. They're at the beginning of the file, and they're in sorted order. So we just scan them till we hit the header page of the index. Right? They're physically sequential, so they don't need to have pointers. They're like right next to each other. It's block 1, block 2, block 3, block 4. That's the leaf level. All right, so it's sequential, index sequential access method. So unlike what we'll see in B+ trees, there's no need to pay for link pointers at the leaf level. The leaf level is physically contiguous on the disk, left to right. Okay. To do an insert in an ISAM, you find the leaf where the data entry belongs, and you put your item in that leaf. And if that leaf is full, you allocate an overflow page at the end of the file, and you stick a pointer to it in the leaf page. And I'll show you a picture of that in a second. In fact, maybe I'll show you a picture to it now. So insert works like this. Let's insert 23. So we start at the... Oh, we walked all the way down. Clearly, it's less than 40. It's between 20 and 33. It needs to go between 20 and 27 at the leaf level, right? But the leaf is full. So what we'll do is we'll allocate an overflow page at the end of the file and put a pointer to it on that leaf page. Know that leaf page is not sorted, or that sequence of leaf pages and overflow is not sorted. Too bad. We'll have to sort it by reading all of that linked list of leaf pages in and sorting it every time we look at that leaf page. You can see why ISAM are kind of 60s technology, right? Nice hierarchical log-based access as long as you never insert anything. Right? And when you start inserting things, we start getting these chains of overflow pages that are in insertion order. They're not in logical order. That kind of stinks. 48, well, it's to the right of 40, so we navigate down to the right. It's to the left of 51, so we navigate down to that leaf node between 40 and 46. It should go on that page. But again, it doesn't fit, so that's got an overflow page. 41 should go between 40, 46, and 48, so we'll navigate to the leaf page where there's room for it on that overflow page. And then 42 is going to create another overflow page. All right, you can see that this data structure starts to degrade upon insertion pretty badly. Right? What's the worst case behavior of this thing, big O notation? Search in this thing in the worst case becomes what after many insertions? O of n, right? In the worst case, you built your tiny little index on your tiny little data, and then you inserted a whole bunch of stuff, creating a giant linked list at the bottom of, say, one leaf page. So almost all your data is in this linked list, and it's not even sorted. You've got yourself a pretty stupid data structure. Okay. So at that point, you rebuild your ISAM. Okay. Now, deletion is, just to go back to the instructions at the bottom here, deletion, go find the item and delete it, so seek and destroy, okay? And if you're deleting a tuple that empties an overflow page, well, that's nice. We can get rid of that overflow page and make the one that used to point to it point to the next one. We can handle the linked list of overflow pages intelligently. So at least in the overflow pages, we'll, reclaim a little data. So let's do our insertions again. Great. And then let's delete 42. And when we do that, we can also delete the associated overflow page and kind of give it back to the pool. Delete 51. Actually, where'd it go? We just delete it. It's just gone, okay? Because it was in that primary leaf page, and that structure is never going to change. And delete 97. Oop. Oh, here's a point. After we delete 51, interestingly, there's still a 51 up above in the index level. We didn't delete it from up above. That's okay. Why is that okay? Yeah. It still acts as a pivot. Nicely said. 51 in this case is just directing traffic. It's pivoting our search to the left or to the right. Sure, it could be any value now between 47 and 55 would be fine there. But 51 is a perfectly reasonable number to have there. Let's just leave it. Moreover, we're not going to change any of the index pages because it's ISAM. Okay? But it's fine. Nothing's going to break. We don't assume 51's in the data. The real data, you have to go to the leaf level to look for it. Right? So unlike the B tree that you might learn about in an algorithms class, the data structures we're going to look at here, both the ISAM and the B plus tree, all the data, the true data is in the leaves, and the superstructure is just navigation. Okay, so keep that in mind. We can have keys up there in the index pages that are not in the data, and that's okay.
Do you have to leave space for a pointer in the memory space to overflow for all of them?
Yeah, good point. So because we may need to chain these overflow pages, every leaf page and overflow page has to have room for one pointer, which is the next pointer in a linked list. Right? So we have to reserve just a little bit of room on each one of these pages to hold a pointer to the next disk block. Absolutely right. Okay, and when we delete 97, we just delete it once again. Okay, so what are some good... Yes, question?
If you go back to before
Before
you deleted the 42.
I deleted the 42... There.
From this state, if we delete a 41, then we still have two stacks.
Yeah, so the question was, and this is in the direction of could we make this silly data structure slightly less silly? Suppose we deleted 41 here. Wouldn't it be nice to kind of compact that linked list of data? So I don't actually know what IBM's implementation of ISAM does in that case. And this is mostly just for our own educational staging. But certainly it would be nice to compact that list, at least to look one level down to one page ahead and say, could we put two pages together? It's a good idea. I don't actually know if they do it or not. You will not be tested on the details of managing overflow lists in ISAM, so implement it as wisely as you like. It's a bad data structure, so don't implement it at all. Okay, it's just to give you an idea. Okay, so here we go. There are some particularly good things about ISAM. There's one uniquely good thing about ISAM that we will lose when we do the B plus tree. Can anybody guess what that is? It's in the name. Sequentiality, yeah, the S, right? So the ability to do a sequential scan on the disk with no random IOs and read off the data in order is a nice thing about the ISAM, right? And that's what they were going for back in those days, I guess, was they wanted to maintain that sequential scan and have some index. All right, that's a nice thing. We're not going to see that when we do the B plus tree in a minute. Okay, we're going to lose that sequentiality. If, for example, this analogy becomes increasingly dated, but supposing you were building an index and you were going to burn it to like a DVD, ISAM would actually be a reasonable thing to do, right? You get it all balanced, you get the data sequentially, you get your index, it's never going to change. So that's not bad. I mean, God forbid you should ever do index searches on a DVD because it'd be incredibly slow. But you get the idea, right? If you had write never data, then ISAM's actually really quite nice because of that sequential I/O. And the cons are obvious, right? We said it degrades to O linear search in the worst case. And in general, it's just going to have overflow chains in bad places. It doesn't handle dynamics gracefully, right? It doesn't handle insertion and deletion. Okay. So let's fix that. The B plus tree, humbly named the B plus tree by its inventor, Rudolf Bayer, who claims it was not named after him. It's the workhorse of basically every database system, all right, is a B-plus tree. It's going to be a balanced tree, much like the ISAM, of blocks. Insertion and deletion are going to be log-base fn cost, so the tree is height balanced. Fan-out is f, the number of leaf pages is n in that expression. The clever thing, particularly when you think back to your 61B or 1970, whichever you prefer to remember, is that this is a balanced tree that is not actually width balanced. It's height balanced, but individual nodes will have fewer or more pointers on them, which sort of, if you do that, interesting. How would you do that? So the way we're going to guarantee our log is we're going to make sure that every node has at least 50% full of pointers. So if the pointers could range between, say, D and 2D, we'll make sure there's at least D pointers on every page. Right? And then, because that's just a constant factor off of 2D, we'll be able to guarantee our log-based F cost, but it's going to give us some slop between D and 2D to play with things. All right? So each node will be 50% or more occupied, except for the root, which is kind of a degenerate case. So each node is going to contain m entries between D and 2D. If you want to sort of talk B-tree talk, I don't know who you would talk this talk to. D is sometimes called the order of the tree. I don't really know anyone who uses that term, but it's in the book and it's in the slides, so there you go. We will talk about the capacity of these pages being between D and 2D, though, right? Because that's basic to understanding the performance of the structure. Right? It's going to support equality and range searches. As in ISAM, all the searches will go all the way to the leaves. So again, those internal keys are not data. They're just going to direct traffic. The classic B tree, which Bayer also invented, the internal nodes contain the data. So you kind of have data hanging in the internal nodes and in the leaves. In the B-plus tree, the data is all at the leaves, which is going to allow us to do scans more efficiently. Okay. So the data is always at the leaves. You walk all the way down to a leaf to find items. Right? You can't trust the data in the internal nodes. It's just for routing you down to the leaves. All right. So it's a lot like an ISAM, but it's a dynamic structure. It's going to grow and shrink elegantly and maintain its log guarantees. So here's how it works. This looks awfully like an ISAM, except now we do have pointers across the leaf level. Why do we need those pointers across the leaf level? To support what? To support scanning a range of values, right? If I say I want all values greater than 22, right? Or I guess in this case, greater than or equal to 24. I need to be able to find 24 and continue to the right. And preferably, I don't want to go bouncing up and down in the tree because those are IOs that I shouldn't have to pay for. Right? So we're going to keep a linked list, doubly linked list actually, so we can do less than queries too, across the leaves. Okay. So search begins at the root and key comparisons directed to a leaf. So if we want to search for 5, for example, you walk down left of 13 and you find 5. If you want to search for 15, you say, is it greater than 13? Yes. Is it greater than 17? No. So you walk down here, and now in the leaf level, there's no 15, so we know the answer to that is no matches. Okay. If you're searching for all data entries greater than 24, you can do a little binary search on the root page to say, it's greater than 24, so we go down here. Remember, the pages, when you look at them, are in RAM, right? Our buffer pool is where we see these pages. So we access the root. Root page gets loaded into the buffer manager. And now we're looking at a page-sized block of RAM. We can do binary search in there, within the page, right? So to find what pointer to use for 24, we can do binary search within the page. It'll point us down here. We look for 24. We find it. And then we return 27, 29. We follow the pointer, get a new page off the disk. We return 33, 34, 38, and 39, right? Okay, so it's down and to the right for greater than and down and to the left for less than. Okay, just to give you a sense of the numbers, okay? So in practice, and these are old numbers from the book, I think. So this is maybe, multiply this by like 16 or 20 or some round number like that to get to typical numbers today. But let's say there's 100 items on a typical page, 100 to 200, okay? 100 to 200 items on a page. Typical fill factor, the same argument applies that we talked about last time, usually about 2/3 full after a sequence of insertions and deletions randomly. So average fan out, let's say, is 133 in one of these B trees, circa 2,000. So typical capacity, just do your arithmetic. A height 2 B tree, 133 cubed, okay, because we're going to get the root, the level below it, and the level below that. That's 2 IOs. Height 2 is going to be 2 million entries. All right? That's a big number. So let's just make sure we understand this. This is a height 0 B tree by the terminology of the book. 133 children. All right, this is a height 1 B tree. 133 children per 133 children. This is a height 2 B tree. All right, and then down here are the pointers to the file, potentially. All right, so this contains over 1 million items. 2 million items. That's a lot. And you only do 1, 2, 3 IOs to get to the leaf level. All right, so that's pretty good. Right? That's why when I said last time, imagine when I talked about index nested loops join, I said imagine that getting a lookup in that index is 2 to 3 IOs. That's pretty realistic, actually, right? Millions of tuples you can get them in 2 to 3 IOs. Also, let's think about, for a minute, and I think I might be jumping ahead, but let's think about our buffer manager replacement policy from last time. Suppose we're using LRU caching, okay? So we're going to replace pages that are least frequently used. And we're doing a lot of B-tree lookups. What's the likelihood that the root is in memory? If we're doing a lot of B-tree lookups. It's really high because every single lookup in the B-tree accesses the root. Right? So every time we touch the B-tree, we go through here. So this thing's going to be accessed for every B-tree lookup. What about this guy? What are its odds of being accessed on a given lookup? 1 over 133 if they're random lookups, right? So maybe not so often, all right? And then down here, it's 1 over 133 squared. It's getting very unlikely. But you can assume that the root, and actually often the second level of the B tree, are just sitting in the LRU cache because they're hot. Which means that really to do an IO, you're like, that was free, maybe 1 IO in the index. And if it's not an alternative 1 index, if the tuples actually aren't here, but you have pointers to them in some other file, then it's another IO to go get them. So B-trees, it's kind of like 1 IO to go get a lookup in a B-tree. It's pretty cheap, right, which is great. It's still a random IO, though. And remember, random IO is 10 to 20 times more expensive than a sequential IO. So you don't want to do lots and lots of lookups in a B-tree. You'd rather scan at some point. Keep that in mind, too. All right, and you can see the numbers. They get really big really fast, thanks to exponentiation. I have religious relatives who have like 6 to 8 children at a time, and when you go to weddings, you get like 3 generations of those families, and they walk down the aisle, and it's just like keeps going, right? Exponentiation's amazing. Okay. Inserting a data entry into a B plus tree. So how do you do insertion? All right. So this is where it gets fussy, and you want to start paying close attention. All right. First, you find the place to insert it. So you do a search. Mark down the tree to find the correct leaf, L, and then you put the item on L, and if there's room for it, you're done. And that's exactly the same as ISAM. Where it differs from ISAM is what happens if L is full, right? You don't create an overflow page. Well, you kind of do create an overflow page temporarily. So what we're going to do is we're going to split that leaf node by allocating a new page and taking half the stuff that used to be on the old page and putting it on the new page. And then moving the new item in the right place in between. And rather than read this, I'm going to show you a picture. Because it's annoying to read the pseudocode, and it's really easy to see in a picture. We'll bounce back and forth. But let's insert 8 into this B tree. So you can see where it's going to go, right? It's going to go in the far left node. So we do binary search on the root, which tells us to go to the far left node. We get to that node. It's full. So let's pretend we're in ISAM for a minute. We'll allocate. First we'll traverse to the leaf. Whee! Then we'll allocate a new page, like almost an overflow page. But what we're going to do, instead of just putting 8 there in a linked list, we're going to take the sorted list of values that's on that page, and we're going to split them up evenly between the old page and the new page, as if we're splitting it in half. So 5 and 7 go there. And now we figure out where 8 goes. So now these 2 pages are both in sorted order. And then rather than making this a overflow page, we want to shove it back into the tree at the same level that the original page was at. We want the tree to remain height balanced, which means that every path from root to leaf should be the same length. Right? But we're going to have ourselves a problem, which is in order to insert a pointer to this page in the root, we're going to need space in the root, and there is no space in the root. So we're going to split recursively. So watch what happens. First of all, we need to know how to point to this new page. What would be a good pointer value? What would be a good key value for this new page? All right, one idea would be 4, which actually would work, but is kind of subversive. There's much easier to take a value we have here, right, which would be 5. Okay, so 5 would be a nice value for this page. 4 would have worked, actually, But what we're going to do is, because it's greater than or equal to logic here, right? You can say 5 will be the lowest value on that page, which was the middle of all the values we had between the two pages, right? That's going to be the key value for this new page. So we need a pointer and a 5, and we need to shove them into the root. But there's no room for that new index pair of 5 comma pointer. So I want to put a 5 and a pointer there, but I don't got no room. So we're going to recursively split the root. And when we split the root, we're going to play the same trick. We're going to allocate another page. We're going to shuffle the values over. Whee! All right? We're going to make room for our 5. Oh, and move the pointers with them, right? So let's do that again. The thing to the left of 24 pointed to the middle page. The thing between 24 and 30 pointed to the second to the right. The thing to the right of 30 pointed to the right, right? So those are all just going to move over, all right? So we really just moved all that stuff. I just couldn't animate moving pointers. It was too hard. And then we want to stick the 5 up above. But, now we've got a tree with no root, which is not going to be good. So this is where the tree actually gets taller, is when you split the root. So we're going to allocate a new root. All right, now we need to split up all these keys. We've got a 5 that's pointing to down here. We got these 2 children. Where does everything go? Well, the root's going to split the tree into halves, right? So we want the middlemost key between 5, 13, 17, 24, and 30 to kind of be pushed up into the root. All right, and it's going to be our split key. So it's going to be, in this case, 17, if I'm not mistaken, is the middle value. That's going to be the differentiator between these two pages. And now we have ourselves a nice, balanced B tree. Okay? So that illustrated the worst case scenario in insertion, which is you go down to the leaf and you recurse all the way up to the root, and the root has to split. And that's when a B tree gets taller. It usually just gets wider, and then occasionally you split the root and it gets taller by one level. Right? And because it splits upwards rather than downwards, you always know every path is the same length. Make sense? Every path is of length k, and then you split the root, and then every path is of length k plus 1. Right? So all paths get longer together by splitting the root. And that's sort of one of those, I never thought of that. All my trees always used to split downward. Never occurred to me to split them upward. But that's how you get the balancing argument in the B tree. Okay? So no rotations, no crazy stuff like that. Just split upward. There is an important distinction that happened that got buried here in this, which is the difference between the leaf level nodes and the internal nodes. And so let me go through that quickly, and then we'll talk it through in the text of the slide. Okay, so watch here when we split this leaf page. It goes there. Now we're going to need to put a key up above. What key are we going to pick? We're going to pick 5. Okay? We're copying that 5. The 5 stays in the leaf node because 5 is real data, and all the real data is in the leaves. Okay? So you never take anything out of the leaves unless the user asks you to delete something. Right? So the 5 stays in the leaves. So when you're splitting a leaf node, you copy its key upwards into the next level. Right? And then we did this, and we did this, and the 5 ended up copied one level up. But watch what happens with the 17, which is an internal key that we're going to move. The 17 actually gets pushed up. It doesn't get copied up because it's just directing traffic, and the place it needs to direct traffic is there. Things less than 17 are down that branch. But the 17 itself doesn't have and shouldn't stay at the level it was at before. Right? So the internal nodes where they're just pivots was the word you used, is a good word. The keys are pushed up. But at the leaf level, key is copied up because it's data, and all the data has to stay at the leaf level. So remember that distinction when you're learning the algorithms for this. And so now, if we go to the previous page with the actual pseudocode, starting from the top, put the data entry on L. If L has enough space, you're done. Else you must split L into L and a new node L2. You redistribute the entries evenly and in order, copying up the middle key to the next level up, and you insert an index entry pointing to L2 into the parent of L with that middle key. All right, this is a little sloppy, the pseudocode, to be honest. And then this can happen recursively, but when you split internal index nodes, you redistribute the entries evenly, but you push up that middle key. And the proper pseudocode is in the textbook, all right? I encourage you to read it. Splits grow the tree, and a root split increases height. So splits kind of go like this, and eventually like that. Tree growth, it either gets wider or it gets one level taller. Okay, so we went through all this. Doom. That's the basic idea of B tree insertion. Cool. All right. So that's what happens after we insert the 8. Okay. Right, we got a root split leading to increase in height. This is the same slide as before, just without the animation, I believe. Now, there's a weird thing, which is that if we really wanted to, there's another way we could have accommodated 8. And it's not unlike the suggestion that was made before about compacting the ISAM pages. If we wanted to make room for 8, we could have sort of shoved it in the second level, the second node from the left, and changed the keys above it or something. We could have kind of consolidated across the leaf level to make room for 8. We could have did that, all right, but it's kind of ugly. And in general, you might have to slosh from way far to the right to make space on the left or something like that. So we don't do that typically in practice. We don't redistribute entries on insertion. Okay. This is just to hammer home once again the difference between copying up and pushing up, and I'll just do it one more time. Okay? So observe how the minimum occupancy is guaranteed regardless. We always have at least 50% full at the leaf level or the index levels because we take full pages and we split them in half. So they always are at least 50% full, right? There's something sort of very elegant about the constraints always being guaranteed here. There's no rotation. There's no like restructuring of the tree. It's just by dealing with things when they're full and then splitting them, we keep our 50% full and things grow upwards and all paths remain the same length. All right. But notice when we split a data page, it splits into 2, and the entry that goes above is a copy of that value 5. That's the entry to be inserted in the parent node. Right? That's the index entry key comma pointer. And with the index page split, we split it into 2, right? But we take that middlemost value 17, and we actually don't include it at the level it used to be at. It's been pushed up into the parent node. So the insertion of the index entry 17 comma pointer takes the 17 away from the node below. Okay? All right. Deletion. Well, starts out just like ISAM again. You go to the leaf level, you find the item, you remove it. Now, unlike ISAM, we have to maintain our constraint of at least 50% full for it to be a proper B tree. So if the leaf is still at least half full, we're done. But if the leaf has fewer than D entries, which in this case will be exactly D minus 1 entries, because this is what's going to happen at that point, we will try actually to do what I said we don't do at insertion time. We can try to borrow some entries from our neighbors at the leaf level. Okay? So you can borrow from a sibling, not a cousin, because a cousin you have to traverse up to the grandparents to find a common ancestor. But we can borrow from a sibling if we share the same parent node. And then we adjust the keys in the parent. Okay? And if that doesn't do it and we still have less than 50% full, then what we're going to have to do is take our sibling, merge with our sibling, and form a new key. All right? It's the opposite of split, essentially. All right? And if a merge occurs, then the entry that used to point to one of the two items that's merged has to be deleted from the parent, which might make the parent under full. And so this might recurse up the tree till, in fact, if the root is emptied, then the tree shrinks. If you merge two nodes below the root, then you get the root being redundant and it shrinks. I'm being a little vague because I don't want you to learn this. Okay? You could learn it. That'd be fine. But we don't implement this in most typical database systems. All right? They actually cheat, and they allow pages to go less than half full. If a page is really, really empty, sometimes you can reclaim the page and just leave the tree a little unbalanced for a while. Why would people do this? This seems horrible. It's just as bad as ISAM, only in reverse. Right? Worst case scenario, we got a giant tree and no data, which is the size of all the, it's log the size of the data we used to have to look up nothing. It just seems weird. Why is this okay? Yeah. In general, people don't have delete-heavy workloads in their database. And even if they do, they're followed by insert-heavy workloads. Usually, if you've grown a table to 1 million tuples or more, it's not going to become a 10-tuple table in the future for a long period of time. Okay? So rather than write this extra code and debug it, and rather than do all the IOs to maintain it, let's just keep the capacity in the tree there for future inserts. All right? This table clearly has periods where it's big, so let's just keep the index big. Right? So actually, it's not worth implementing this stuff. As an academic exercise, you might want to know how it works, but I will not quiz you on it, all right, in this class. And, it's not really actually that important. Okay. There are 4 hidden slides in the slide deck you can download and go look at if you want, or you can read the book. For fun, I Googled for B plus tree visualization last night, and in fact, there's a pretty nice one on the web at USF, actually, which is kind of cool, University of San Francisco, right across the bay. It kind of looks like this. So here's a little B tree. It's got 20, 30, 40, and 50. It's got a degree of 5, so it can hold 5 things, and we can insert something in it. We can insert, what should we insert in it? I don't know. 10. Great choice. Hey, look at that. All right, let's insert a few more things. 200, 11, 100. Hey, look at that. All right, you can play with this. It's quite handy, actually. There's only one minor distinction that I found last night goofing around with this, with our book and slides, which is upon deletion, it actually, when you delete a node from the leaf, it'll update the split pointer above it. Remember in ISAM, we deleted something and there was like a 15 left over above, and I said that was cool? So these guys will actually run around and fix the things above to match. So I'll show you an example. Let's delete 50. Watch the key value in the root. If we delete 50, it updates the root to have 100. There's no need to do that. That just adds extra write traffic to the database. At some point, we have to flush that page with the 100 on it now because it's dirty. And it really hasn't helped us any. All right, so this is a little obsessive-compulsive about deletion. I think that's the only difference, though, between this animation and the algorithm in the book. Okay, so it's actually pretty good, really helpful, and in fact, I think we might make you play with this on your vitamin just to kind of get you to visualize these splits and insertions. So, all right. Typically, if you want to implement a B tree, you want to get that fan out as big as you can. What's the goal of making the fan out bigger? Yeah. It makes the tree shorter sometimes, right? Yeah. So it postpones the point at which the tree grows, would be another way to say it. You can absorb more insertions before you grow. And yeah, if you have a data set that kind of rides the boundary between, say 2 and 3 levels, if you get more fan out, you can keep it at 2 levels. Right? And that can be kind of a big win because instead of every lookup being, say, cache it, 1 IO, it might just be cache it, no IOs. Right? It can make a huge difference in your performance. So we try to make these things have as big a fan out as possible. What can we do to increase the fan out of our B tree? Well, we could have bigger pages, right? Now, there's always some sort of trade-off between having big pages that you don't really look at most of. But the page size is going to be the same for lots of data structures in the database. So you could pick a page size that's really big, but then you'll often fetch pages and only look at a subset of them. Or you can pick a page size that's really small, but then you get lots of IOs, right? And so it's kind of a toss-up. So page size usually gets tuned up and kind of fixed. And let's say it's 64K, we don't get to adjust it. So we can't change the page size. I just ruled that out after thinking about it. But there is more that we can do to increase the fan out. We can't change the physical storage, which means what we've got to do is shrink the stuff we're putting in it. All right, so rather than changing the page size, we're going to compress the stuff inside the page. We're going to try to use compression to jam more B tree entries onto a page. All right, so I'm going to teach you 2 little tricks for compression. The goal is to get more entries per page, therefore to get shorter trees. All right, the first is what's called, these are annoyingly called prefix and suffix compression. They could have easily been named the other way around. I'll try to be on exams, we'll try to make sure we indicate which one we mean. Prefix compression, remember that these key values just direct traffic, so we really don't need all the details. So here's some key values from the book. They're kind of maybe a little overly verbose. Like this would be just as good, don't you think? They're distinguished from each other. They're in alphabetical order. Why not? Why not just compress? Is it right? I mean, did I mess anything up? Let me ask you a different question. Is it the same? Is this thing the same as that? Would it direct traffic exactly the same way? Well, let's take an example. Let's take David Jones. David Jones. Where do I go to find David Jones in this tree? The 1, 2, 3rd pointer between Davy Jones and David Smith, right? All right. Well, on this tree, where do I go to find David Jones? The 1, 2, 3, 4th pointer. So it's not the same. But is it bad? Not really. Not as long as all the data is in the right place, right? As long as all the pointers point to data where the data is. I don't mind if it's balanced slightly differently. We're still got 50% fan out, okay? And so now things are a little bit further to the right than they used to be or something. That's fine. It's all balanced anyway. Okay, so it's not the same exact thing, but it is just as good, and it takes up less space. And so here's the thing, is we just need to make sure the data is in the right place, and that, it turns out, comes for free. Because the way that compression happens is you do it when you split the leaf. So when I split a leaf node and it's got lots of long strings in it, the key that I'm going to copy up is going to be the shortest thing I can copy up that's differentiating. So think about it this way, and I don't think I have a picture of this in the slides. Let's say I have a node that I'm splitting, and it's got, I don't know, halfway through this node there's a value, George Gershwin. And the next value is George Washington. All right, when I split this page, if I split it here, I'm not going to copy up George Washington. I'm going to copy up George W. That's enough to distinguish. And from now on, this is compressed up the tree. All right, this is as long as this needs to be ever again. We'll never see George Washington higher up. So the compression happens upon the copying up, right? And the pointers all point the right way, right? The invariant that the pointers are all correct happens the minute you do this insertion. So we're all good. You don't compress the existing tree. You compress as you copy up, and everything works out. Okay? The other thing you can do, which is just like straight up compression, it's called suffix compression. If you have a whole bunch of things on the same page that have a common prefix, well, shove the prefix in the corner and then just put the distinguishing suffixes there. So instead of writing down McDonald, McDougall, McFeely, McLaren, you just write down, hey, Mac, and then Donald, Dougal, Feely, Laren. All right. The reason that this isn't just sort of a dorky hack is that we often have composite keys, right? So remember, we might have an index that's defined on, say, last name, comma, first name, right? And maybe this doesn't even merit a picture, but if we have a page, where those are two different columns, but we're going to have composite keys in our index. So there's going to be, Jones, comma, Davy. That's one key. And Jones, comma, David. That's another key, etc. Because there's going to be lots of Joneses, right? You pull that out as a separate prefix, and then you just store the suffixes. Right? It happens all the time when you have these composite keys, because the first field that you index on may have lots of duplicates. Right? Last name, comma, first name. There's lots of duplicates on last name. Right? So this is a pretty typical optimization you want to do. Make sense? All right. One more topic, I think, on B-trees. Actually, maybe before I do this, let's take a little stretch, and I have some announcements. So this is sort of a different thing. I even took notes. All right, before you have too much fun, I don't want you to start like a long conversation. Homework 2. So I would like to make a brief announcement about homework 2. Homework 2 is due Thursday night at 11:59 p.m. We've been known to have certain tolerances for lateness in the order of a minute here and there, but the official deadline is 11:59 p.m. To avoid confusion over what really is 12 o'clock and what day is it on. So Thursday night at 11:59, the homework is due. After that, you start accruing slip days. In homework 1, a number of people struggled to get the correct incantations with Git to submit the homework properly. We were lenient in homework 1. In fact, Michelle is in the process of painstakingly and by hand being extra lenient. We're not going to do that in homework 2. So if in homework 1 you got a 0 because you mis-submitted with Git, please learn your lesson, because in homework 2 you will simply get a 0, all right, and no amount of complaining will save you. Right? You have been warned. All right? So learn from any mistakes you made in homework 1. Autograder? By tomorrow morning, Derek promises, with a smile on his face and a late night ahead of him. By tomorrow morning, there will be an autograder installed in the cloud, if you will, although it'll probably be in Evans. Evans? No. Soda. Yeah. Wow. I'm really old. I went to grad school in Evans. When you do a git push, you'll be able to see if your tests ran properly tomorrow when you do your git push. The autograder should be installed. So it's going to actually run the same tests you run now, no additional tests. Right? But it'll run the same tests you have in the infrastructure and get back to you with email? Yeah. With email saying that your tests ran and here's the outputs. So you should be able to tell if your git submit is working. Okay? But we will have no patience for people who don't get that process correct when you submit. So really important to understand how you submit with Git. If you do not have a question, yeah. The blue shirt and then, so behind you and then you.
Are those tests that run just like a subset of like real tests and get graded?
Yeah, there will be additional tests we're holding back because in the real world when you ship software, you don't get all the tests as your test suite. The real world comes back and says, hey, you have a bug and now you have to give me a refund. Yes? Group repository is what's going to get graded. Won't fire up the autograder. Yeah. Right? Good. So you must submit to your group repository to get the autograder going. If you submit to your personal repository, your class individual repository, the autograder will not go. All right, partners for homework 2. If you do not have a partner, it's awfully late, and you're required to have a partner. And so if you do not have a partner, you'd better be in touch with the TAs like Prontissimo. There will be perhaps some way to do some speed dating. But boy, it's really late. But it's required to have a partner to get a grade on this homework. And if you feel that you are in an exceptional situation for some reason, please come contact me or email me immediately. And it better be a pretty good reason because it's not that hard to get a partner. Okay. And just for a minute, having a partner is good, right? Pair programming is good. You get fewer bugs. It's good for your humility because actually people point out your mistakes. So all that stuff is good. I think as engineers, we all need a little training in socialization, and so being forced to actually work with another person who maybe you don't even know, that's good experience too, right? I know you do this in your other classes anyway. It's a good thing to do. We don't require it for all the homeworks, but I do require it for this one, even though probably, yes, you could do it all by yourself because you're an awesome Berkeley EECS major. Okay, I get it. I still want you to partner up. Okay. Piazza. So a couple comments on Piazza. In the interest of helping the staff prioritize answering questions on Piazza, if somebody asks a question, please don't respond with, yeah, I don't understand that either. Either respond with an answer or don't respond. Because what happens is we tend to jump to the questions that have no responses first. Right? And say, oh man, nobody's ever answered that person. I feel so bad. And so we'll jump in and we'll start responding. But if, that happens through like an automatic, was there a response or not? And then we'll start reading through all the posts and seeing what's going on. But as a matter of prioritization, please don't fill in the responses unless it's actually an answer to the question. Okay? It just helps us prioritize responding on Piazza. Okay. So with that, I actually want to take a pause before we do bulk loading and we return to lecture. Any administrative questions before we go on? Yeah.
When you are splitting the page, you're always copying the middle element. For future lookup, when you are searching the exact same value in the page, are you putting that?
Okay. That was not an administrative question, but I will answer it. But just give me a minute. It's here. Did anybody have any organizational questions? Then we'll get back to B-trees. Yes?
If you or your partner do not have any slip days, but the other member of your team does have all the slip days.
The eternal slip day question. So the question was, suppose that you have no slip days left and your partner has many slip days left. How does that work? It's a good question when you have a mixture of solo and group projects, right? It works the way the rules say. So you, hypothetically, if you're late, will start losing points, and your partner won't. All right? Which means that you and your partner should have a long talk. Yeah. Yeah. So the incentive structure around slip days and points and everything is individual, but it may incent you to work differently with your partner than otherwise. All right? Other administrative questions? Okay, and then feel free to post to Piazza if you have one that occurs to you. So let me answer the question about B-tree insertion, which has a pretty short answer, and then I want to talk a little bit about joint algorithms, which is a refresh. So the question was, well, let me give the theme, and then maybe the principle behind the answer, then I'll ask the question and answer the question. So remember in the B-tree, an index entry, which will be something like 5 and a pointer. What that's saying is that, and then let's say there's 10. The things on this page are greater than or equal to 5 and less than 10. And the things on this page are greater than or equal to 10, etc. All right. I probably shouldn't put these in the page because this is a description of what's in the page. It's not actually the contents of the page. There's stuff in here. That stuff is greater than or equal to 5 and less than 10. This stuff is greater than or equal to 10 and less than something. Okay, so this 5 is a greater than or equal to pointer, which means that when we split, and so the question was on split, how do we make sure to find the item that we copied up? The item that we copied up will always be just to the right. It'll be the first entry of the split key. So let's go through the example in detail. We'll take a leaf page. Here's our leaf page. It's got 3, 4, 5, 10. All right. Well, we'll just do it like that. And then we want to insert, say, 11. Okay? So we want to put 11 here, so we'll split it. We move 5 and 10 to the right, along with 11. And by the way, when we break ties, typically we'll have sometimes an odd number of things to split up. The odd-numbered thing, the higher-numbered thing will go to the right as a convention, just so we get the same answer when we do these examples. All right, so if it's like 5, we'll do 3 to the right and 2 to the left. If it's 121, divide it by 2. And yeah, anyway, we round up over here. All right, so the 5 is here, and the thing that's copied up is 5 as well. So the new key that gets inserted in the root is 5 pointer to this thing. Okay? So it's always, because it's greater than or equal to, it means that this thing is going to be over there. All right. So I want to spend a moment revisiting index-nested loops join, which one of you came to office hours today and pointed out to me the pseudocode in the slides is kind of ridiculously dorky and unclear. And now that we know how indexes work anyway, let me review quickly. So, oh wow, blast from the past. I guess I use the board more than other people. All right. So index-nested loops join. We are scanning one table. Let's do a concrete example. Here's our query. Select student dot last name, comma, course dot name from, and I know we haven't learned join syntax yet in SQL, but you'll figure it out as I go here. Students S courses C, where the student ID in the students table is the same as the student ID. Oh, you know what? This is not courses. Excuse me. This is the enrollment records table. E dot course name. Enrolled E equals E dot SID. So I want to find all pairs of students and enrollment records where the enrollment record is about that student, right? And I want to know for each one the last name of the student and the name of the course they're enrolled in, okay? So I'm going to do this with an index-nested loops join, and I'm going to have an index on the enrolled table on that SID field, all right? And it's going to be an alternative to index from last time, which means that here's the enrolled heap file. It's a plain old heap file. That's where the enrolled tuples are. And here's going to be the students heap file, which is smaller because each student has many enrollment records. Okay? And then I'm going to build a B tree, which is alternative 2, which means that in the leaf levels, what we'll have are, it's going to be a B tree on e.enrolled.sid. And so in the leaf level, what I'll have is I'll have SID, comma, record ID pairs that point into the enrolled heap file. Right? So you'll be able to look up SIDs in here, and when you find the SID you like, there'll be a pointer to the tuple in the enrolled table where you can go get it. Okay, that's an alternative 2 index. And this thing is a B tree, so it's going to be, I don't know, let's say 3 levels deep. Okay, so it's going to have a root, it's going to have a level here, it's going to have a level here, and it's going to have... Okay, yep. 3 levels deep. Okay, so index nested loops join is going to look like this. Well, let me animate it, and then we'll write it down. Scan the student table. For every record of the student table, do a lookup of the SID in that record, in this index, to find matching enrolled records. Right? So you get a student, you walk down the tree, 1, 2, 3, 4 requests to the buffer pool, maybe only 2 of them are IOs, and then you follow a pointer to get a record ID out of here. Each student may be enrolled in many courses, so every time we grab one tuple out of here, there may be 3 or 4 matches here, right? Which we're going to fetch with get next one at a time, okay? And so the algorithm for index nested loops join actually does have a nested loop in it, despite the index, but it's a little nested loop over the matches. So the algorithm should look like this. For S in student, matches equals B plus tree lookup student dot SID semicolon for enroll dot SID, right? For E in matches, of which there may be more than one, right? Return, S comma E. So this little call here is not in the pseudocode in the slides, which seems like a pity. Okay. And what is this call B tree lookup? It's the walk down the tree, right? And it's in this pseudocode we're finding all the matches and putting them in a set. In practice, we implement this with iterators, all right? And maybe that's an exercise we'll leave for a section or another day. But you should think about, if you had to do this with iterators, how would you do it? I'll just give you a hint. It's the same question for plain old nested loops join. How do you implement it with iterators? But basically, we're going to say, here's a join iterator. Here's an index lookup iterator. Here's a scan iterator. Scan students. This thing's going to say next to get a student. It's going to say pass that student ID down here to get a next lookup. And it's going to keep doing that, getting next lookups and feeding them to the output until it runs out of matches. And then it's going to get another student and do the same thing again. So I'll let you guys think about how you do this with iterators. But hopefully the algorithm for index nested loops now is clear. Okay? Yeah, is that, no? All right. So in the time remaining, let's finish up our B plus trees. The last detail, which is actually an important one. Remember how I said we built an ISAM by taking a full table and then sorting the data and creating the ISAM above it, right? So this is actually a fairly standard thing. You're like, you know what? I have this big table, and I'd like to add an index, maybe an alternative 2 index, on one of the columns. So I already have a lot of data, and I want to quickly build an index. It's very inefficient to repeatedly run the insertion algorithm for B trees on each row of that million tuple table. Why is that? Why would it be a bad idea to just run insert over and over and over? Well, it's slow, and it also has poor leaf space utilization. All right, but why is it slow? Why is it slow to do multiple inserts? Well, think about the I.O. pattern, particularly if the data is not sorted yet, right? You're walking down a B tree, which in steady state is half full, let's say. Halfway through, it's half full. So it's a B tree of some size, and you're doing random lookups in it to do the insertions. Well, these random lookups will hit cache on the root, but as you get down to the bottom, it's doing random I.O.s and inserting a single tuple on each one of those pages. So you're getting a random I.O. per tuple of insertion. That's expensive, right? You want to get a whole page full of goodness out of that random I.O., and you're getting one tuple of goodness. So what we want to do is come up with a scheme where when we do an I.O., we load that page full of data, right? So if we're going to look at a leaf level of this index, let's put all the tuples that go on that page at once. So it's called bulk loading. And so this is, it's going to be really slow. It's order the number of tuples, number of I.O.s to do insertion. It's going to be order the number of pages of the file to do it properly with bulk loading. All right? So a factor of 100, 200 faster. Also, and this is something you may want to play with that web animation. If you do insertions, you can't actually, it's very hard to get the leaf level to stay full. It tends to want to get half full, or really 2/3 full is what it gets sort of stochastically. If you really want to pack up a B tree nice and tight, because the data set's not going to change much, well, then you're going to have to control it some other way than insertion, because insertions are going to tend to kind of split the pages right when you didn't want them to split. All right. So, and you can play with, you'll see this if you try doing insertions into this. Actually, I challenge you to do this. You go to the web animation, make up values to insert so that you can keep your B tree nice and compact. It's actually like, you got to start making up values like in between things. And of course, that's not how the real world works. You don't get to make up your data as you go. You have to actually deal with the data. All right, so bulk loading is going to be better. So this is the deal. Take your file and run sort on it. External sort algorithm that we all know and love, right? So that's going to be read the file, write out batches that are sorted, read the batches back in, right? When you're reading the batches back in, so that's the output of the merge algorithm, we're going to bring it into memory and pages. It's going to come in an order, okay? And what we're going to do is we're going to start, imagine we're reading the sorted pages back in. They're actually streaming in from the sort algorithm, but you can imagine them being on disk in sorted order. We're going to take them a page at a time and start building a superstructure of a B tree above them. So we'll take the first page of sorted things and we'll put a root above it. And that's how we get started. And we haven't read any of this stuff in this box yet because it's coming streaming into us from a sort algorithm. Okay. And then what's going to happen is as more pages come in, we're going to be basically in steady state. We're going to have a partially built tree on the prefix of the sorted order, like on the upper right here, right? So at some point we've read all the way up through 36, and we've built this thing above it. And then by induction, what we're going to do is we're going to take the next page load of stuff, and we're going to start inserting it at the end onto new pages. So 38, 41 will go together, and we'll insert those two into the parent right there, all right? And then we'll just recurse. And what's going to happen is we're always inserting to the right of this tree, and the leaf level is always exactly as full as we want it to be. We can make it not totally full if we don't want it totally full, or we can make it totally full if we want it totally full, okay? So we can control the compactness on the leaf level, and we're always inserting things to the right. And the tree IOs are going to only grow leaf pages when we can fill them up completely. All right, so each leaf page gets visited exactly once in this thing. What about the parent pages, though? Like, is it a problem that we're doing these insertions toward the right? Well, let's think about LRU. What pages do we tend to touch when we do an insertion to the right? Well, we'll touch the root and all the children to the far right. Yeah? Which means that the next time we do that, it's still going to be the root and the things to the far right. And we'll have a lot of locality on the right fringe of this tree. The right fringe is always what's hot. And the left part of the tree sort of gets colder and colder and gets paged out. Right? Which is great. So LRU is going to do the right thing here. As we insert these things to the right, this right fringe of the tree is already in cache, and life is good. Right? So this is going to have the behavior we want, which is that we're going to visit each page on the disk pretty much just once, right, to fill it up. And then it'll get written down when it gets evicted from the buffer pool. Okay, so this is going to be a pretty nice bulk loading algorithm. There are other bulk loading algorithms. This one's pretty good. And it happens to be in the book. All right, so this exercise I kind of walked you through, but you may want to convince yourself that it's true. All right, multiple inserts is slow. Bulk loading is good. The leaves are stored. Actually, so here's a detail I didn't point out. You can actually get the effect of an ISAM Because when you start streaming the data in to the leaf level, you can store it on the disk in a new file, right? You can make that leaf level be pages 0, 1, 2, 3, 4, 5, 6 of a file. And then you can write the index pages later somewhere else in that file. And so you get actually a file where coincidentally, after doing this, the B tree organization looks a lot like an ISAM. The front of the file is a bunch of pages that are sequentially in order, which is great. Keep in mind that it's not a guarantee. So we still need our pointers, our linked list at the leaves. But if you start scanning the leaves, like on a range query, say you're doing all things greater than 6, as you follow these pointers, you'll say, hey, guess what? This is page 2, and I have a pointer to, page 3, which is right under the disk head. Oh, look, page 4, that's right under the disk head too. And so you are following pointers, and if things are messed up, and not sequential, that's fine. But if they are sequential, you'll get nice locality on the disk. Right? So you can actually create a leaf level that is sequential on the disk, even though we don't promise it's sequential. Right? And the only cost we pay then are these pointers, but the sequentiality is under our control when we load the bulk loading. So that's kind of cool. And then, as I said, you can control the fill factor on those leaf pages. If you want to leave room for future inserts and make them 2/3 full, great. If you want to make them 1/3 full, you can do that too. It's entirely up to you how you fill out that leaf level. If you want to make it really packed, you can make them 100% full. But it's under your control. All right, a little detail. We said that the order of a tree D, that every node would have between D and 2D entries, meaning pointers. Okay? But in practice, when we use key compression or variable-sized keys like strings, the entries on those keys, the keys on those entries will be of variable size, which means you'll have more or less of them on a page depending on the data, right? So you might have a long key here and then a short key and then a long key. So the index pages may hold lots more entries than the leaf pages because they're compressed. And by the way, remember alternative 3 from last time? So that's where in the leaf page you have a key like, suppose you're indexing popular words on the internet and you have the key Perry. And these days that has lots and lots of matches. We'll store them all in a set, right, of RIDs. This set's going to be super long, right? So this key is in essence super duper wide because of all those pointers. So even at the leaf level in alternative 3, you get variable length. Popular keys are wider than less popular keys. So we actually can't guarantee this order D thing exactly. Some pages will just have lots of items, and some pages will have few items. So instead, as an approximation, we'll just talk about the page being physically half full of bytes. Right? It may be that it's half full of bytes because you have a few big things, or it may be half full of bytes because you have lots of small things. And yes, that matters a little, but let's assume it's in the noise. Okay? And as I said, many real systems don't even promise you to be half full anyhow. They'll let you get less than half full. All right. But the nice thing about the order stuff is it gives you that big O guarantee that you wanted, and it gives you the sense that you're doing something robust. Lots of times in practical computer science, after you prove something, you then cheat a little bit, and it all works out in the wash experimentally. Okay? To summarize, and hopefully this will be useful, these summaries, and so please don't get up and leave and disrupt your peers. Tree-structured indexes, they're very nice for unidimensional, one-dimensional range search. They're good for equality searches as well, and because of that combination, they're very widely used. ISAM, strictly of historical/pedagogical interest. Okay, it's a static structure. The only thing that changes are the leaf-level pages have insertions and deletions, and overflow pages, right? Remember the organization of the ISAM file where the data is stored sequentially at the beginning of the file, and I drew it vertically on the slide, right? But here's a whole bunch of data rows, and then when you're done with the data, which is ordered, then you start storing the internal nodes, or the index entries, they're called. And then at the end of that, and this all is fixed, this never changes. Well, the data pages can have insertions, and deletions, but they don't actually change the number of pages. The overflow pages are here, and this is where the action is in the file, right? Going from left to right. The overflow chains obviously can cause performance to degrade to as bad as linear. The B+ tree is a dynamic adaptation where inserts and deletes leave the tree height balanced with n items, log base f of n cost, where f is the fan out of a node of the tree. A high fan out means the depth is rarely more than 3 or 4 in practice, which is great. This is almost always better than maintaining a sorted file for any number of reasons, including binary search is expensive, and including that maintaining the sorted file is more expensive than maintaining a B+ tree. On average, it works out that things are kind of 2/3 full in a B+ tree, so you want to account for that when you think about what F really is in practice. It's about 2/3 of the possible occupancy. Almost always you want a B+ tree instead of ISAM because it's a dynamic structure. So almost nobody uses ISAMs. Now here's a detail buried in the last bullet of the summary. We didn't talk much about alternatives 1, 2, and 3 today. So actually, let's take a minute and do that, since we do have a minute. Oh, we don't have a minute. We'll take a negative minute, and next time I will come back and elucidate the last bullet of the slide. Oh, and there's more, but I think we're good. Lions. See ya. Good luck with your homework. Get cracking.